Good morning, everybody. Thank you for the introduction. Yes, it has been a very long 24 hours, but I'm glad to be here, and I'm glad to be presenting to you today. Okay, so I'm going to tell you a little bit about my story of how we have taken plasmid DNA into manufacturing. So a little bit about me, my history. I am a medical microbiologist by qualification, but my love for bacterial fermentation started about 8 years ago when I was introduced to a bioreactor and I had no idea what this bioreactor did. And I spent my nights studying every line that went into the bioreactor, as in your chilled water in, chilled water out, steam in, steam out. I tried to figure out every line. So that's where my love came from. So I am based at Afrigen Biologics. We are based in the beautiful, beautiful Cape Town in South Africa. So welcome to how we have scaled up our plasmid DNA process. Okay, so what I'm going to cover today is who Afrigen is, what's our purpose, and the partnerships that we have currently. And then we'll go into plasmid DNA and why it is super important for us. And I'll then talk about our small-scale studies and how we had scaled up from shake flasks to a bioreactor. And then I will talk about how this product, Bacto CD Supreme, the supplementation and the feed has impacted our processes at Afrigen. And then I will go on to the conclusions. Okay, so Afrigen is a biotechnology company based in South Africa. And the purpose and the mission of this company was to ensure that vaccine manufacturing was established on the African continent. And it aims to support Africa's vaccine production capacity by promoting the technology transfer, the skill building, and the infrastructure development to foster self-sustained biotechnology sector. So the initial technology started with vaccine adjuvant and formulation innovation. It then moved on to end-to-end mRNA vaccine technology development, and we had to ensure that Africa was in a position to be able to supply vaccines to the continent. So after we have now established an end-to-end, we would then take it to a GMP licensure, and then we would then be able to get the vaccine onto the market. So the WHO had assigned the mRNA Technology Transfer Hub to Afrigen to create the Center of Excellence and Training by building the mRNA vaccine production capacity on the African continent and other lower middle income countries. So partnering with global organizations such as the WHO, CEPI, IVI, and some global suppliers, Afrigen enhanced its research capabilities, helping Africa participate actively in the global research ecosystem. So just in a nutshell, Afrigen was established as the training center for these lower middle income countries. So all development happens at Afrigen, and the lower middle income countries, who I will show you in a bit, then come to Afrigen, get trained on the process, and then take that knowledge that they have learned into their various countries. Okay, so Afrigen's historic journey in 2014 to 2015, it was established by the Industrial Development Corporation, which is IDRI, to localize production capacity for the TB vaccine. In 2017, the first adjuvant was created and formulated in Africa. And then in 2018, the development of the adjuvant platform into products through vaccine innovation partnerships. In 2019, the innovation around the adjuvant formulation platform was developed and formulated for health products, more specifically for animals and CBD at Afrigen. And then in 2020, We started our first construction of the R&D laboratories and the adjuvant manufacturing suites to operationalize the startup business. So Afrigen is a startup. We're still very, very small. We're about 150 people. So we've been growing since then. And then in 2021, we were contracted by the WHO and other partners to be the global mRNA technology transfer for the lower middle income countries. And then the R&D and facility construction started in November of 2021. And we take it to 2022 to 2023, the facility construction occurred and the preparation of the GMP licensure of the end-to-end, which is restricted at the moment to the drug substance and the drug product vaccine manufacturing facility in Q2 2025. That's happening this week. Actually, we're getting a GMP license this week. So just a little bit about the technology transfer program. WHO and MPP have established Afrigen as the technology transfer hub. So in South Africa, we've got our first partner as BioVac. I actually used to work there, and that's where my love started. And then I moved on to Afrigen. We then have other countries like Kenya, we have Brazil, we have Indonesia, we have a whole host of covering four continents, and these are the countries that are involved in the technology transfer hub. Is anybody from these countries? No? Okay. All right, so by November 2023, 14 of the 15 partners had received the mRNA development knowledge transfer from Afrigen. And by this month, we would have completed 12 out of the 14 partners with the technology transfer demonstration and the hands-on training. So it's been a busy, busy year for our drug substance and our drug product teams. Okay, so just to chat a little bit about the conventional mRNA process. Of course, we have our starter material, our plasma DNA, and our plasma DNA has our gene of interest. It then gets transformed into E. coli, and then it gets purified to remove the host cell contaminants. It then moves into your in vitro transcription. It has to be linearized first, and then goes into your IVT where it's capped, and then therefore moving on to, purified, and then moving on to your formulation into lipid nanoparticles. As we know, mRNA is not stable on its own. It has to be formulated into lipid nanoparticles. And then we then move into sterile filtration and aseptic filling. But the scope of today will be on the beautiful plasmid production. All right, so what is pDNA? Plasmid DNA is a small circular piece of DNA that acts as a carrier of the genetic information. And it is widely used in biotechnology to produce proteins, vaccines, gene therapies, you name it. So why does it matter? So the pDNA serves as the starting template for producing mRNA vaccines. The DNA sequence carried on the plasmid contains the genetic blueprint for the antigen, and in this case, the spike protein of SARS-CoV-2. So this process that I'm going to run through today was built off SARS-CoV-2 spike protein. The plasmid is then used in vitro transcription, as mentioned in the previous slide, to synthesize the actual mRNA, which is then later formulated into the vaccine. So the importance of it for the mRNA vaccine, the foundation of production, without good quality pDNA, we don't have reliable mRNA. The purity, integrity, and the yield of the pDNA directly affects the vaccine safety, potency, and the scalability. So if we have bad quality pDNA, we're going to get bad quality mRNA. If your yields are low with your pDNA, you're going to get out low yields of your mRNA. And pDNA is the second highest cost contributor to mRNA vaccines. The first is the lipid nanoparticles, but plasmid DNA is also very, very expensive to produce. The scalability and the speed, the plasmid-based systems allow fast design and scale up, which is critical during pandemics. And as we know, in a pandemic, it is best to act fast. Once the plasmid design is ready, millions of doses can be produced in a matter of weeks. Regulatory compliance, the GMP-grade plasmid ensures that downstream mRNA is free of the contaminants, which is endotoxins, host proteins, and your host DNA. It guarantees that your vaccines will be safe for human use, and with using the products that we've been using from Thermo Fisher, we know that they are GMP-grade ready. And the versatility of this platform is that it can be quickly adapted to produce different disease target mRNA vaccines. And one of the things that I'd like to mention is that in building a process, your process has to be robust enough so that you can plug in any disease target. And since we've built this process of SARS-CoV-2, we have plugged in other disease targets, and I'll show you some data a little bit later. All right, so the objective of what we try to do here is can Bacto CD Supreme, with the addition of the supplement, assist in the evaluation and development of a robust small to large scale pDNA process? Can scaling up with the use of Bacto CD feed enhance yield and quality via your fed batch cultivation? So can we use CD feed to actually help our productivity? And to compare pDNA yield and quality between the conventional LB versus Bacto CD Supreme. A lot of studies were done in-house by myself to actually test between LB and Bacto CD Supreme. And then we needed to compare the pDNA yield and the quality between Bacto CD Supreme versus Bacto CD Supreme with the addition of the supplement. Okay. All right, so the study design, I'm just going to chat a little bit about our glycerol stocks. So this might be a little bit of a trade secret, but I didn't say anything here. Glycerol stocks are extremely, extremely important in your cultivation. So I know that I've had lots of chats with people regarding how they make their glycerol stocks. And one of the things that I've heard is that the media is inoculated into, the culture is inoculated into the media and it's left overnight to grow and it's banked the next day. That is not good because if you are banking your cells that are already in stationary phase or your death phase, which has been growing for 16 hours, you are starting with a low amount of good, healthy cells. So it is very important to ensure that when you are banking your glycerol stocks, they are banked in their mid-exponential phase. So how this was done was that we had taken glycerol stocks of our working cell bank. We had a master cell bank, and it was then passaged to make our working cell bank. And we had taken 2 of the stocks and inoculated into 2 tubes each and grown for, I'll explain that in the next slide. It was inoculated into 25 moles media and incubated and then split into half and half. So that equated to between a 5 and a 6.75% inoculation into your 200 moles of media. So this slide I'm going to explain briefly. This can be a little bit confusing, but I'll go through each one. So the small scale optimization is that we ran 9 experiments, small scale, to identify key things, and that is what media would be the best to produce the highest quality and the highest yield of pDNA, what temperature would be the best to produce the highest quality and the highest yield, what cell line would give us the highest quality and the highest yield, and what harvest time can we now harvest the culture to get the highest quality and the highest yield. So experiment 1, I had read a couple of papers before I had started this process, and a couple of papers had mentioned that 42 degrees Celsius, and our gentleman there had mentioned that you had extremely high titers when you had increased it to 42. I started with 42 degrees Celsius. So the shake flask went into the incubator at 42 degrees Celsius. and I harvested it between 8 and 9 hours. Unfortunately, our yields were extremely low. And we had poly-A instability, which means that our poly-A was actually truncated after testing it, and we had seen that we did not get good quality pDNA from there. Experiments 2, 5, 7, and 8, they were grown at 37 degrees Celsius, and experiment 2 was grown for 9 hours, 5 for 16 hours, 7 and 8 for 20. So our yields were moderate to high, and we had found that CD Supreme compared to LB was the highest producer of the pDNA concentration. Experiment 3, we used another E. coli strain, and we had grown it at 30 degrees Celsius for 9 hours, but unfortunately we got quite low yields in that experiment. And we had actually noticed that LB was the highest producer of pDNA concentration, which was strange, but results are results. And then experiment 4 and 6, we had done the same strain, and we had grown it at 37 degrees, experiment 4 for 9 hours, experiment 6 for 20 hours. We had gotten moderate to high yields. And to note, CD Supreme was the highest producer of the pDNA concentration. And then experiment 9, since we had deduced some good results from there, experiment 9, we said, let's try some supplementation and see how that affects our culture. So we had grown it at 37 with strain 2, very similar to this experiment, but we had, of course, spiked it with the supplement, and we had extremely high yields. And CD Supreme, with the addition of supplement, was the highest producer of pDNA concentration. So this is experiment 1, which was the 42 degrees Celsius experiment. We used E. coli strain 1, and this was comparing LB versus CD Supreme media. We had taken samples every hour, and this was the average of the 4 flasks. So you'll see quite a large variation in our results here. So this is your LB, and this is your CD Supreme. This was 42 degrees Celsius, right? So, and these two is your concentration for LB and your concentration for CD Supreme. So it's very interesting to note here is that after this experiment, we had purified samples via the mini prep, and we had seen a massive jump. And at that point, I thought, eureka. But unfortunately, it wasn't a eureka moment. So back to experiment, well, still at experiment 1, it's showing our gels from our poly-A analysis. This is time point hour 1 to 5, and you'll see that this is our normal expected poly-A band and our sizing. So we would expect our band at 455 base pairs. Just mind the little bit of a up and down there. We do make our gels in-house, so there would be some slight changes in the band sizing. So we had double digested the plasmid, and the yellow is your LB media, and the blue is your CD Supreme. So this is what it's supposed to look like. We then see after time point 6 in LB medium, we had some poly-A truncation here. And the same with time point 8 with CD Supreme, we had some poly-A truncation. So I'd just like to go back. So T6 and T8, we've seen an increase T6, and we saw an increase T8. So that was the truncation of the poly-A. All right, so how can we compare LB and chemically defined medium? For the batch-to-batch consistency, we saw a very high batch consistency with chemically defined, and whereas for nutrient broth, there was high variability due to undefined components. Reproducibility for chemically defined, it was excellent for the process development and scale-up, but for the nutrient broth, there was poor reproducibility across the batches. Downstream processing, we saw fewer impurities with chemically defined, whereas for the nutrient broth, there was more host cell proteins and impurities that we had to remove. In terms of scalability, it was highly scalable with controlled performance with chemically defined, and scale up may lead to variability in performance with LB. Cost, it's more expensive. But down the line, it works out to be higher yields, which could bring your cost down eventually. Nutrient broth, cheaper, and it's much easier to prepare. We know exactly what goes into it, but at the end of the day, there's more steps that you have to add to purify your pDNA. The overall cost, potentially low due to the downstream burden, and your LB broth potentially high due to the yield inconsistency and your purification costs. All right, so this experiment was comparing just the normal CD Supreme versus CD Supreme with the addition of supplement. So here we see this is your CD Supreme. This is capturing your optical density at 600 nanometers. So CD Supreme media, fairly low optical density, whereas with CD Supreme, with the addition of supplement, it boosted it a little bit in terms of the cell density. And this was grown at 37 degrees as our standard process for our shake flasks. Then we checked the concentration of the pDNA from the CD Supreme and the CD Supreme with the addition of supplement. CD Supreme, plain CD Supreme here, and the addition of supplement. It is quite varying because we did use mini preps, so the results can vary a little bit. But you can take an average from here and you can see that your concentration was a lot higher when you added your supplement. Okay, then we moved on to bioreactor batch. So from this method, in the shake flask, we had come to the decision that CD Supreme was the best performer, and we had also come to the conclusion that the addition of supplement would give us higher yields. So we then moved on to batch mode, which is just inoculating the vessel and leaving it. And we had seen that our bioreactor batch 1 was quite high, bioreactor batch 2, lower, but around the same, and then bioreactor batch 3 as well. So you'll see that we had sampled every hour, so the breaks are where we were sleeping. And you'll notice that there is a little bit of a dip here. This was super interesting to us. We had seen it went into stationary, and then it picked up again. So I don't know if this was the supplement, but I think it is, that it has that little boost of nutrients, and then it starts to grow again. So from this 3 batches, we were then able to learn how the consumption of our glycerol was occurring, and we started off with an initial concentration of 10 gram per liter in our media, and we had then waited for it to decline. So our consumption of our carbon source, again, our carbon source was glycerol, starting off at 10 gram per liter known concentration. But I think as we had added the supplement, it may have increased. So this was done by HPLC method, and you'll see a gradual decline in your glycerol concentration. So with papers, normal papers state that you start feeding when your glycerol is at around 0.1 gram per liter. I tried it, it didn't work. So I just needed to know this as information purposes, but I'll cover in the next slide that our first batch was a fail. But we learned a lot from that, and we had then ran more fed batches, and we had learned a lot. So for our fed batch bioreactor, as I said, we were under the impression that we had to feed when your glycerol is at 0.1, which took it around about to 30 hours post. inoculation. So I had then decided to feed at around 13 hours for the first fed batch. Unfortunately, those results are not in there because they won't look good here. It will skew the results quite a bit. But it did not work for us, unfortunately, because our oxygen demand was very high at the time, and we were not able to maintain our dissolved oxygen rates. Our dissolved oxygen percentages, sorry. So the yellow is our fed batch 2. The light green is our fed batch 3. The blue is our fed batch 4. And this one, fed batch 5, is another disease target. So we've got an N equals 3 for the first 3, and then we've got fed batch 5, which is another disease target. Insane amounts of plasmid that we had extracted from fed batch 5. All right, so I want to talk a little bit about the oxygen transfer. As we all know, living aerobic cells need oxygen. However, with our current system in our R&D facility, we did not have oxygen-enriched air. So we were working with pure compressed air, which is 21% oxygen. It was really difficult to maintain our oxygen, our dissolved oxygen at 30% in our first fed batch. As mentioned before, we had started feeding at 13 hours post, and our dissolved oxygen plummeted, and there was no way to bring it back up. So fed batch 2 went fairly okay. We just saw some spikes here and some drops here due to the arch nemesis of fermentation, which is your antifoam. So you'll see towards the end, this is antifoam addition that kept dropping it. Fed batch 3, we came in the morning and we saw the foam was gone all the way to the top of the vessel. We had then put in a little bit of antifoam, and it had plummeted. So at this point, I made a call and said, harvest it immediately. Fed batch 4 and 5 went very well, except here, antifoam did a number on us here, but it maintained really well. One of the things that we had to ensure was that our cells had enough oxygen, so we had to increase our aeration and our stirrer to quite high values. With E. coli, you can go up to 1,200, but our process was maintaining at around 1,000 RPM with the cascade. And the VVM, we increased it to around like 5, which is quite high. But because it's not oxygen-enriched air, we had to increase it regardless. And just to state here that scaling to fed batch, we had achieved up to a 4 times higher concentration without the loss of the quality, which is a very, very rare balance. All right, so the summary of the bioreactor batches, batch 1, 2, and 3, we used CD Supreme plus the supplement. And with this, we had starting concentration of 10 gram per liter. All grown at 37 degrees standard. And then the optical densities at the time of harvest was around 13, 10, and 12. And our pellet weights here was 33.2 grams, 26.84 grams, and 31.32 grams. Let me come this way. And then our estimated yields was quite low. So we had taken our milligrams extracted by our liters per hour. And then to fed batch 1, which was the learning curve, we had grown it at 37 degrees, and then we had harvested our optical density at 31.73, which was really high, considering the fact that we didn't get a lot of yield out of it. Our pellet weight was really high because of our cell density, and our yield was 10.85. And the reason being was because we had plummeted the dissolved oxygen. It sat at about 1% dissolved oxygen for about 6 hours. So not great plasmid yields. And then our productivity, of course, quite low. And then fed batch 2, we had the normal CD Supreme with the supplement and the feed. I then started thinking of how can we change this method. So we had grown it for 30 degrees, we had grown it at 30 degrees, and we had induced it to 42 degrees when it had reached its stationary phase. Our optical density was quite high, was 29.5, and our pellet weight was quite moderate, 51.76, but our yields were fairly high. Our volumetric productivity also fairly high. Fed batch 3 and fed batch 4, similar, but we had noticed a big change here. And if I go back, fed batch 3 is the one that plummeted, but fed batch 3 got out quite high yields, which was interesting to know. Fed batch 4, we had obviously repeated, and we had seen that we had gotten out fairly moderate, but not as high as the previous run. And then fed batch 5, which was another disease target, we knocked it out of the park. And I think this yield in milligrams was fairly high, considering we only harvested about 1.3 liters. And then just to see it on a bar graph, this is the yields, and you'll see fed batch 5, which was another disease target, our productivity was very, very high. So the process impact for Afrigen is that we had established a scalable and a reproducible pDNA process from 200 ml shake flask to a 1.5 liter fed batch. We had improved our yields and our quality, and which is creating a foundation for the scale-up. We had also maintained our plasmid stability, preventing our unwanted isoforms. So when we had checked our gels, we had seen that we're getting around 80% plus supercoil form. And then our cost and efficiency, it reduced our trial and error through optimized media and feeding, and we had higher productivity per run, so which means that there's a lower cost per gram of pDNA. And our competitive advantage is that we had strengthened our end-to-end mRNA platform. So where we have an established drug substance and drug product process, we now have a process to scale up so that we can become end-to-end within Africa. And it positioned Afrigen as a leader in mRNA vaccine development. We are the first people within the lower middle income countries to actually develop this pDNA process. And our collaboration and growth, we had validated that Thermo Fisher Scientific product in real-world studies actually works. And we had built credibility for future partnerships and knowledge transfer. So with every mRNA hub partner that comes to site, I always take them through the process. It's just a brief overview of how we start from transformation all the way up to 200 ml shake flask. And I always tell them that throw away LB and move to CD Supreme. So by integrating CD Supreme and CD Feed, we had shortened the process development time and gained more of a reliable upstream foundation. And what are the future directions for us? We're going to move from 1.5 liter, which is in our R&D facility, to a 20 liter bioreactor in our production facility. We're going to position ourselves as a CDMO eventually when we get our GMP license for this process on the production floor, and we will then start manufacturing for whoever wants to buy pDNA, because currently we are buying pDNA from European countries, and of course, as an African continent, it is quite expensive for us. So to position ourselves to become our own manufacturers of pDNA would be really good standing for us. And then our process optimization, we have to refine our supplement dosing and our feeding strategies. So once we move onto the production floor, we have an oxygen line in there. So our process is going to look very different. We will have to optimize, and we will have to maintain. I'm sure it will be much better than when we did our fed batches in our R&D. And then we will become GMP ready as well, and we will evaluate our critical quality attributes. As mentioned before, we have to get higher than 80% supercoiled. And we must reduce our endotoxins and our residual host proteins, and that is via our purification processes. So we will apply this platform to other disease targets. We've only tested one disease target, but as we move forward through the process, we will plug in the other disease targets. And so far it's worked, and I have very, very, very positive thoughts about us making this process work for every other disease target. I will mention though that we have tested a number of disease targets in small scale, and we have noticed that there is a slight difference depending on the size of the plasmid. So the size of the plasmid will give us lower. The higher the size of the plasmid, the lower your pDNA concentration is at the end. And then collaboration, to partner with Thermo Fisher Scientific for upstream product refinement and a case study or even a publication for this. And yeah, expanding to other plasmid backbones and moving towards GMP readiness. Hopefully we can do this together. So our impact slide here. Our small scale optimization, we tested LB versus CD Supreme versus CD Supreme with the supplement. We have tested strains, cell lines, temperature, time of incubation, and the result is a plus 300% yield when using CD Supreme with supplement in our small scale optimizations. And then for fed batch bioreactor systems and our studies that we had done, we had to manage our oxygen transfer and our nutrient limits, and our result was that we had a four times yield increase and a very, very stable plasmid. Just a note on that, when we are doing a clonal selection, so I'm going to take you all the way back now. So when you are doing a clonal selection, that is after your transformation, if you're going to cultivate your cells and you do it in LB compared to CD Supreme, we've noticed that an overnight incubation of LB truncated a plasmid, whereas if you put it in CD Supreme, you don't get any truncation of your plasmid. All right, and then back to your high quality for pDNA, for GMP manufacturing. Our supercoiled DNA is most important, especially for our IBT process. That was maintained. And the scalability and reproducibility of our process using this media was really good, and the result is that we have a robust process. So by integrating CD Supreme and the supplement and the feed into our plasmid manufacturing workflows, we achieved unprecedented yield and consistency, underscoring its promise to transform upstream processing in biomanufacturing. And our conclusions is that we have a process that is now established, and we have developed and optimized a scalable pDNA production process. Significant improvements is that CD Supreme enabled much higher yield and purity as compared to LB media. CD Supreme enabled higher yield compared to CD Supreme with the addition of supplement. I think that is supposed to be the other way around, actually. Our CD Supreme with the addition of supplement gave us higher than just the plain CD Supreme. And then the combination of CD Supreme with the addition of supplement and CD feed had enabled high yields and purity in our bioreactor system. And our critical insights is that we had identified key variables, which is our media, our host strain, temperature, time of incubation, that drive the performance. We had recognized our process limitations and our lessons learned to guide the improvements for future scalability and consistency. So again, with our fed batch 1, we know that from papers it says something, but in real life it does something else. And then our impact was that the results directly support the mRNA vaccine workflows, and our process improvements aligned with our GMP readiness and the scale-up potential, so which positions us really well for vaccine preparedness for the continent. And our collaborative value is that we demonstrated real-world validation of this media. So my acknowledgements is thank you very much to Thermo Fisher for providing the samples and the technical support that we had received. Really, really great as the collaboration had gone on. And every time I had an issue, I would just schedule a meeting with our experts, and they had guided us through. And our funders, NPP and WHO, and our partners, NIH, NIAD, and the VRC. The VRC had actually assisted us with some of our scale-up work as well. And my team at Afrigen for the support and the dedication to the innovation and the continuous learning. I had some crazy ideas, my team went with it, and I'm really grateful to them. Thank you.